Hello everyone, this is lecture 6, the inverse of a square matrix, or for short, the inverse of a matrix. So in this lecture, we're going to learn how to define the inverse of a matrix, learn the definitions of the inverse of the matrix, and learn the technique to find the inverse of a 2 by 2 matrix using a formula. And then we're going to learn that can apply Gauss-Jordan elimination method to obtain the inverse of a matrix. Then later, we're going to use the inverse to solve the system of linear equations. Okay, so first, let's start with the definitions of inverse matrix. From the last two lectures, we focus on matrices and properties of matrices. And one particular property, very important property, is that the matrix multiplication is not always commutative. So that means if you have A times B, it's not going to be always equal to B times A. There are some special cases that the equality occurs. That means A times B equal to B times A. That particular case is for inverse matrix. So let's write down the definitions of inverse matrix. So if A is an n by n matrix, an inverse of A is also an n by n matrix, and I call this matrix B with the property that A times B equal to an identity matrix, or in this case, the identity matrix n by n is also equal to B times A. So again, where I n by n is the identity matrix of the signs n by n, if such B exists, you say that then A is invertible. Okay, so again, the definition in this case that if you have a square matrix, n by n by matrix, and if you have another vector another matrix, an n by n matrix, and you do the product, and if you get the identity matrix, then B is the inverse of the matrix A, or A is invertible in that particular case. So for the first example, given the matrix 2, 5, 1, 3, and another matrix 3, -5, -1, and 2, they want to show that B is the inverse of A. Of course, to do that, what you do is you can write A times B, or this is 2, 5, 1, 3 times 3, -5, -1, 2. And you do the matrix multiplications for these two matrices. So what you got is 2 times 3 plus 5 times -1. Then the next entry is 2 times -5 plus 5 times +2. And in the second row, the first entry is 1 times 3 plus 3 times -1. And the second entry is 1 times -5 plus 3 times 2. And of course, you obtain the 2 by 2 identity matrix, 1, 0, 0, 1. Right. So with this calculation, it shows that B is the inverse of A. So this shows that B is the inverse matrix of A. All right. As a matter of fact, A is also the inverse matrix of B. If you do the calculations, B times A, you will see 3, -5, -1, 2 times 2, 5, 1, 3. And you also going to obtain the identity matrix 1001, right? So in this example, A and B are inverses of one another. Okay. So when you find the inverse of the matrix, the result of the inverse is unique. So there's only one inverse for every matrix. So if A is an n by n invertible matrix, is an n by n invertible matrix. So invertible matrix indicates that A has an inverse. And then is inverse is unique. And we denote the unique inverse as A -1, right? So this is indications of the invertible matrix, or sorry, the inverse of the matrix A. All right, so we're gonna quickly prove this particular theorem. So this is the uniqueness of the inverse of the matrix. So the proof is as follow. So we use a proof by contradictions, right? So we use a proof by contradictions. To show that the inverse of an invertible matrix is in fact unique. Right. So we're gonna do this or prove this by contradiction. That means first we make the assumption that, or suppose, A is an invertible matrix. And it has two inverses, namely A1 and A2, right? So in this case, we make the assumptions that, okay, A is an invertible matrix and there are two inverses. The first one, A1, and the second inverse is A2. Then by definitions, you have that A1 times A is equal to identity matrix, right? Because A1 is the inverse, so it's multiplied with A, get the identity matrix, or it is also equal to A times A1. And similarly, because A2 is assumed to be the inverse of the matrix as well, so you get A2A times I equal to A times A2, right? Then what you have is that I'm gonna do A1 equal to A1 times the identity matrix. So if a matrix multiply with the identity matrix, it's gonna give you the matrix itself. But the identity matrix can be equal to A times A2, right? So A1 times A times A2. Right, so I just basically substitute the identity matrix by the product A times A2. Now I'm going to use associative properties of matrices. I get A1A times A2, right? And this particular product is actually the identity matrix again. So identity matrix multiplied with A2. So this is equal to A2, right? So this calculation shows us that A1 is actually equal to A2. Therefore, you can conclude that the inverse of the matrix is unique. Right. Therefore, the inverse of matrix A is unique. Okay. So again, you only have one inverse of any given matrix. All right, so I have three different remarks here. The first one is that not all square matrices are invertible. Right, so you cannot always find the inverse of a matrix, right? A matrix is not invertible. That means you cannot find the inverse of the matrix is called a singular matrix. Right. And an invertible matrix is called a non-singular matrix. An invertible matrix is called non-singular matrix. All right, so hopefully you could be able to distinguish between singular matrix and a non-singular matrix, right? So let me be careful here. So for a singular matrix, that is the matrix is not invertible. And in the case of non-singular matrix, the matrix is invertible. Okay, so hopefully you can see the difference there. In general, matrix multiplication is not commutative. It's not commutative. Right, so we know that's fact at this point, right? Thus, the inverse of A, if exist, must satisfy the conditions that A times B equal to B times A and equal to the identity matrix. Okay. And the last remark I want to mention here is do not attempt to write A inverse over equal to 1 over A. Right, so this is a wrong calculations, right? Because there is no such operations. Okay, so the inverse of a matrix is just the inverse of a matrix. There's the procedure for you to find the inverse of the matrix. It's not going to be 1 over matrix A. This is not the case. Okay, so the next theorem I want to give you is a formula for you to calculate the inverse of a 2 by 2 matrix. The formula only works for a 2 by 2 matrix if you have higher dimensions of matrix, the 3 by 3 or higher. Then you have to follow certain procedure, more specifically Gauss-Jordan eliminations method, to obtain the inverse of the 3 by 3 or 4 by 4 or 5 by 5 matrix. Okay, so for the 2 by 2 matrix, the theorem is if the matrix A is of the form A, B, C, D, then A is invertible if AD minus BC is different from 0, in which case we have that A inverse is equal to 1 over AD minus BC times the new matrix D minus B minus C A. Okay. If you have AD minus BC equal to 0, then A is not invertible. Right. So you have to imply one conditions here that AD minus BC is different from 0 because this expression is in the denominator and we don't want the denominator to be equal to 0. So therefore, if AD minus BC equal to 0, then A is not invertible because the formula will not exist. Okay, so let's do some quick calculations to find the inverse of the following matrices. So A is equal to 1, 2, 3, 4. Then A inverse is 1 over AD minus BC. So the product of the main diagonal subtract the product of the off diagonal. So 1 times 4 minus 3 times 2 multiply with matrix. So A and D get swapped. So you get 4, 1. And you take the negative, you put the negative for the value of B and C. So this is -2, -3. And a quick calculation for the denominator here give us A inverse equal to 1 over negative, sorry. So -1/2, right? Multiply with 4, -2, -3, 1. So this is the inverse of A. Now for the matrix B, you get the matrix of the form 12, -15. 4, -5. And the inverse can be calculated as 1 over 12 times -5 minus 4 times -15 multiply with -5, 12, 15, and -4. However, if you do the calculations for the expressions in the denominator, you will find out that the denominator is equal to 0. Therefore, B is not an invertible matrix. But the calculations 15 times -5 minus 4 times -15 give us 0. Then B is not invertible. Okay, so at this point, hopefully you get some idea how to calculate the inverse of a 2x2 matrix, right? And again, when you have the denominator AD minus BC is different from 0, then the inverse exists or the matrix is invertible. If the denominator is equal to 0, then the matrix is not invertible. Okay. So next, I'm gonna write down some properties of invertible matrices. And there are 5 properties that we might want to know. So suppose A is an invertible matrix, then A inverse is also invertible. And the inverse of A inverse is the original matrix. Now, if you have a non-zero scalar C, if C is a non-zero scalar, then C times A, then you take the inverse, is going to be equal to 1 over C times A inverse. Right. So in the previous, one of the previous remarks, we don't have this particular operations that 1 over the matrix. However, in regular calculations that we have so far in mathematics, you do have this calculations of C to the -1 means that you take the reciprocal of C, 1 over C times A inverse. Okay, so hopefully you can see that the difference. So if you have 2 invertible matrices, so A and B are invertible, matrices, then A times B is invertible. And the properties of this is, so A times B inverse is going to be B inverse times A inverse. Now for the case of a transpose, right? So if A is an invertible matrix, then A transpose is also invertible. And the inverse of the transpose is equal to A inverse, and then take the transpose of the inverse. Okay. Now, if you want to calculate the power or find the inverse of the power of a matrix, right? So A to the power n is invertible for all non-negative integers n. And A to the power n, take the inverse of A to the power n is equal to A inverse then raised to the power n. So these are the properties that you may want to know for invertible matrices, right? So keep in mind, at some point we're going to use that to some problems. Okay. The next property is quite important. It's called cancellations properties. So I say that if C is an invertible matrix, then the properties below are true. Sorry about this. Are true. Okay. So if A times C is equal to B times C, then A is equal to B, right? This only works for the case of C is an invertible matrix. Right? And this is called the right cancellation property. Because C is on the right of A and C is also on the right of B. So therefore, there is a case for invertible matrix C, A is equal to B. Okay. Now, in the second situation, if you have C times A equal to C times B, then A is equal to B as well, and this is called the left cancellations property. Okay, because why is left cancellations? Because the matrix C is on the left of A and C is on the left of B as well. All right, so in the next sessions, we're going to learn how to find the inverse of the matrix using Gauss-Jordan eliminations method. Okay, so I know we have the formula to find the inverse of 2 by 2 matrix, but for this particular example, I want to actually use Gauss-Jordan method to obtain the solution of, or to find the form of the inverse of the matrix A. Okay, so because the 2 by 2 matrix is a lot easier to show, a lot similar to understand. Okay, so bear with me here. So the setup for the to find the inverse of the matrix using Gauss-Jordan eliminations method is to form again the augmented matrix, but now is of the form the matrix A that you want to find the inverse of, and the identity matrix of the same side of A. Okay, and you're going to perform elementary row operations, right? So this arrow indicate that you're going to have multiple elementary row operations, and eventually it will come down to the augmented matrix of the form, the identity matrix on the left-hand side of the vertical line, and whatever left on the right-hand side of the vertical line will be the inverse matrix of the matrix A. Okay, so let's do a quick example here to obtain the solution, to obtain the form of the inverse of the matrix 2, 2, 2, 0. All right, so first I'm going to form the augmented matrix of the form 2, 2, 2, 0. And then on the right-hand side of the identity of the vertical line is the identity matrix 1, 0, 0, 1. All right, so we're going to turn or find the reduced row echelon form of this augmented matrix. What you need to do is to look at this, right? And to turn this into a 1. So I need a 1 here. And to do so, you're going to multiply row 1 by 1/2 to create a new row 1. All right, so you have 1/2 times 2 is 1. 1/2 times 2 again is 1. And 1/2 times 1 is 1/2. And the last entry is 0. We didn't make any changes for row 2, so you have row 2 remains the same. Okay. Now you have a leading one in the first row already. That means the element below it or the entry below it has to be equal to 0. So we need a 0 here. And to do that, we're going to do the following row operations. That you borrow the first row and multiply it by -2. Why is -2? Because you want to get rid of this +2. So -2 times row 1 plus row 2, create a new row 2. All right, so you just borrow the first row in this case. So you didn't actually make any changes in the first row, so the first row remains the same. 1/2, 0. But you make the change in the second row. Let me be clear here. This is row 2. Okay, so -2 times 1 is -2 added with +2 becomes 0. -2 times 1 is -2 added with 0 becomes -2. -2 times +1/2 is -1 added with 0, you get -1. And then -2 times 0 added with 1, you get +1. Okay, so that is a new matrix. Now we have the leading one in the first row and the entry below it is 0. Now moving on to the second row. So that is, you need to find the leading one here. So I need 1 here. And to do so, going to multiply row 2 by -1/2 to create a new row 2. Row 1 remains the same. Then row 2 becomes 0, 1, +1/2 and -1/2. Okay, so you have a leading one in the second row. Now that means the entry above it has to be 0, so we need 0 here. And to turn that into a 0, you require the following operations. You borrow row 2, so times, take -1 times row 2 plus row 1 to create a new row 1. So you didn't change anything in row 2, just borrow it. So you have, this is row 2. Now for row 1, you get what? You get -1 times 0 is 0 plus 1 is still 1. -1 times 1 is -1 added with 1 is 0. -1 times 1/2 is -1/2 added with 1/2 becomes 0. And the last entry here is -1 times -1/2 is +1/2 added with 0. You get +1/2. Okay, So you start with the augmented matrix of this form, where you get that this is A, matrix A, and this is the identity matrix. After a bunch of elementary row operations, you obtain the identity matrix on the left-hand side of the vertical line and some matrix on the right-hand side of the vertical line. And that matrix, this matrix right here, is the inverse matrix of capital A, of the matrix A. Right, so we say that the inverse of A is a inverse equal to the matrix of the form 0, 1/2, 1/2, negative 1/2. Or you can simplify the writing a lot much easier by taking 1/2 as the common factor. You get 1/2 here, and we're left with 0, 1, 1, negative 1. Right, so that's the inverse of the matrix A. So in the next example, we have a 3x3 matrix, and we're going to use the Gauss-Jordan eliminations method to find the inverse of the matrix. And we're going to do this by hand as well. Later on, we're going to go back to Python and use the command of reduce row echelon form to actually obtain the inverse of the matrix much easier. But I want to show you the process again to how to use Gauss-Jordan elimination method to obtain the inverse of the matrix by hand. Okay. All right. So you have the matrix A right here. You need to form the augmented matrix of the form. All right. So 1, negative 1, 1, 0, 2, negative 1, 2, 3, 0. And big vertical line, and on the right of the vertical line is the 3x3 identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so you have a leading one in the first row already, which is good. Now for that means the entries below that this leading one has to be equal to 0. This is 0 already, so we're good. Now we need to turn this into a 0, so need a 0 here. And what we do is gonna do take negative 2 times row 1 plus row 2 to create a new row, row 3 in this case, to create a new row 3. All right, so row 1 and row 2 remains the same. So 1, negative 1, 1, 1, 0, 0. Then 0, 2, negative 1, 0, 1, 0. So negative 2 times 1 added with 2 becomes 0. Negative 2 times negative 1 is positive 2. Added with 3, you get 5. Then negative 2 times 1 is negative 2. Added with 0 is negative 2. So on and so forth. The entry in this row is negative 2, 0, 1. Okay, so we're done with the leading one in the first row, and the entry below it has to be equal to 0. Now moving on to the second row, right? That means you want to turn this into a leading one. So we need 1 here. Okay, so to turn that into a 1, you just basically multiply row 2 by 1/2 to create a new row 2. That means row 1 and row 3 remained the same. And so row 3 is 0, 5, negative 2, negative 2, 0, 1. And row 2 now becomes 0, 1, negative 1/2, 0, positive 1/2, 0. Okay, So you have a leading one in the second row. Now that means this has to be 0, right? So the entry right above that has to be 0. The entry below it has to be equal to 0. So let me start with -1 up here. So need 0 here, right? And as well as over here, we need 0 here. Right, so there are two different operations that we need to perform in this particular step to turn these two values into zeros. Okay, let me start with the first row. Okay, so to turn -1 into a 0, what you do is you borrow row 2, right? So 1 times row 2 plus row 1, create a new row 1. So row 2 and row 2 remains the same. Now row 1 becomes, so 1 times 0 is 0 plus 1 is still 1. 1 times 1 times 1 is +1 added with -1 is 0. 1 times -1/2 plus 1 is +1/2. And then so on and so forth. This is 1, this is +1/2, this is 0. Okay, so that's the new first row. Now we need to turn this 5 into a 0 as well. Well, what you do is again borrow the second row and you multiply -5 with row 2 added with row 3 to create a new row 3. So you get, right, so -5 times 0 added with 0 becomes 0. -5 times 1 is -5 added with 5 becomes 0. -5 times -1/2 is 5/2, and then added with -2, you have +1/2, and so on and so forth. This is -2, this is -5/2, and this is +1. All right, so we're done with the leading one in the first row, the leading one in the second row, and the entries above and below that are 0. We move on to the third row. We want to turn this into a leading one as well. So what you do is you multiply row 3 by 2 to obtain a new row 3. So again, in this case, the step row 1 and row 2 remain the same. So 1, 0, 1/2. This is 1, 1/2, 0, 0, 1, -1/2, 0, 1/2, 0. And for row 3, you got 0, 0, 1, -4, -5, +2. Okay, so you have the leading one in row 3. That means the entry above that has to be equal to 0. So we need 0 here. And we're going to borrow the third row when you do the calculation for to turn these two values into zeros. Okay. Right. So let me do row 1 first. Right. So you want to turn this into a 0. What you do is you multiply it, take -1/2, multiply with row 3, add it with row 1 to create a new row 1. Row 3 remains the same. And row 1 is now equal to 1, 0, 0. And you get 3, 3, -1. And to turn this value into a 0, right? We borrow row 3 as well, but what we do is you take 1/2 times row 3 plus row 2 to create a new row 2. And you're going to see that you have 0, 1, 0. Then the entry is -2, -2, 1. Right. So at this point, we obtain on the left hand side of the vertical line, a 3 by 3 identity matrix. And on the right hand side of the vertical line is some matrix, and that matrix is the inverse of A. So that is the particular procedure that you need to follow to obtain the inverse of a 3 by 3 matrix using Gauss-Jordan elimination method. As you can see, there's a lot of steps involved, and you have to be careful when keeping track of all the calculations and the entries in the augmented matrix. So you have to be careful when you do this by hand. Okay. So of course, it's a lot easier for us to do using the Python language. Okay, so let me turn to Python to do some quick calculations using reduce row echelon form command in Python. Okay, so this is the setup that I have. So on the right hand side is the code that I'm going to the environment where I'm going to type in the code, and on the left hand side is the lecture note that we've been working on. So to start a new file, I'm gonna click on new and then click Python 3, and I'm going to change this into lecture 6. Okay. So similar to the last couple of last few lectures that we use Python to do with matrices and whatnot, what you do is I'm gonna import in NumPy and SymPy to help us deal with the comment into linear algebra. So from NumPy, import everything. And here from SymPy, I'm going to import everything. Right. Now I'm going to create an augmented matrix of this form. Remember, in Python, you cannot use the vertical line to separate two matrices. So we just going to create a matrix of the size 3 by 6. Okay. So the idea is to create a 3 by 6 matrix of the form. So let me call this some augmented matrix C is equal to array. Right. So the first row include the entry of 1, -1, 1, 1, 0, 0. The second row include the entry of 0, 2, -1, 0, 1, 0. The third entry or the third row is 2, 3, 0, 0, 0, 1. Let's quickly print this matrix out just to make sure everything is correct. So it works. Now, what you want to do is to obtain the reduced row echelon form of this augmented matrix. What we do is we use matrix C dot RREF, means reduce row echelon form, and we're just going to take the first entry of the output. And this is the reduced row echelon form of the inverse matrix. And as you can see, if you do a quick comparison between the information we got in the note and the information we got in the code, they are matching. Okay. Another way to actually obtain the inverse of the matrix without using the symbolic code is to use the following command. So let's say you have a matrix A of the form. Right? So the original matrix we get is what? 1, -1, 1. So 1, negative 1, and 1. The second row of matrix A is 0, 2, negative 1. And the third row is 2, 3, 0. So let's print this matrix out. So it works. Okay, so comment this out. The command that I'm going to use is, so I'm gonna give it a name. So AINV means that I want to find the inverse of A. And commands for command for the inverse in Python is len alg. So this means linear algebra. Dot INV mean inverse of A. And then you want to print out this particular inverse matrix. So A inverse, hit Shift Enter, and this is the inverse that we're going to have without the augmented matrix. Okay, so here is the matrix. So 3, 3, negative 1, negative 2, negative 2, 1, negative 4, negative 5, and 2. So either one should work for us, but in practice, most of the time, they will use len alg dot INV of the matrix A. Okay, so I give you two options to actually obtain the form of the inverse of a matrix. Either one should work. So in the next example, I'm going to use the right cancellations and left cancellation properties to obtain the representations of the matrix X in the following matrix equations. Right. So I'm going to start with something simple first, and we're going to increase the difficulty as we go along. All right, so in the part A, problem A, you have the matrix equations of the form A times X equal to B. And of course, A, X, and B are matrices. Okay, now to obtain X by itself, what you can do is, if you, for regular mathematics, you can divide both sides for A to obtain capital X. However, in this case, for matrix equations, what you have to do is you have to get rid of capital A. And the way to do that is you do the left multiplication with the inverse of A to obtain the identity matrix on the left-hand side of the equations. So what I do is I'm going to do A inverse AX, right? Because you do the left-hand multiplications for A inverse, you have to do the same for the right-hand side as well. So A inverse times B, and A inverse stay on the left of B. Now, this product will give you an identity matrix. So this implies that identity matrix multiplied with X equal to A inverse times B implies that X equal to A inverse times B. That is how you obtain the representations of X using left-right multiplications or left-right cancellation properties. All right, so the next equation is X times A inverse equal to A to the third power. Now, because A inverse is on the right of X, what you do to get rid of A inverse is to multiply both sides with A, and do that for the right-hand side, the right multiplications. So that is X times A inverse times A equal to A cubed times A. And again, this product is equal to identity matrix. And therefore you have X times I equal to A cubed times A, or X is equal to A to the fourth power. All right. Now, in the next matrix equations, you have AX plus C equal to B. So you have to move C to the right-hand side first, because before you can do the left multiplications to get rid of the matrix A. So now this matrix give me AX equal to B minus C. And because A is on the left of X, to get rid of A, I'm going to do left multiplications of A inverse AX. This is A inverse times B minus C. This give me identity matrix times X equal to A inverse times B minus C, or this is going to be X equal to A inverse times B minus C. All right. So part D and E is going to be a little bit more difficult. So you have to use multiple properties to first expand this inverse. Okay, and let's see what happened. Okay, so we're gonna use the properties of inverse for this product. So this give me the left-hand side become X inverse times A inverse inverse. And on the right hand side, I'm going to expand this inverse as well. And this is going to give me B inverse inverse times A inverse times A times B square. Okay. Now on the left hand side, what you have is A inverse or inverse of A inverse going to be the matrix A itself. So A inverse times, sorry, X inverse times A equal to B times, this is the identity matrix, times B square, right? Or X inverse times A equal to B times B square, or X inverse. Now, to get rid of the A, and again, A is on the right of X inverse at this point. So to get rid of A, what you do is you do the right multiplications. Right, and we get that. Right. And this product give me an identity matrix, and therefore A inverse is just going to be B cubed times X inverse equal to B cubed times A inverse. Now, to get rid of this inverse, you just take the inverse on both sides of the matrix equations, and you get X inverse of that equal to B cubed times A inverse inverse. Or you have X equal to B cubed times A inverse inverse. All right. So that is the form of X in this particular equations. Of course, you can go further, but let's not go do that. It just stop right here. Again, the idea of this exercises is to manipulate different properties of the inverse and different property of left multiplication, right multiplications to obtain the representations of the matrix X. Okay. In the next example, you have A inverse times BX inverse equal to A inverse times B cubed square. Okay, so I'm going to move A inverse to the right hand side. To do that, because A inverse is on the right of this product. So what I'm going to do is I'm going to do left multiplications on both sides of the equations. And I'm going to expand this square as A inverse B cubed times another A inverse B cubed. Okay, so this gives me an identity matrix. Therefore, the left-hand side become BX inverse. And for the right-hand side, these two matrices can be combined together to get to produce an identity matrix. All right, so you have identity matrix B cubed, A inverse, another B cubed, or of course this is just B cubed times A inverse times B cubed. All right, now I'm going to expand this product using the property of the inverse. So that is X inverse times B inverse equal to B cube A inverse B cube again. And to get rid of B inverse, this B inverse is on the right of X inverse. So what you do is you do the right multiplications. Right. And this give me an identity matrix, and you get just X inverse equal to B cubed times A inverse times B to the fourth. And to get rid of the inverse, you just take the inverse on both sides of the equations, and this is what you get. So B cubed times A inverse B to the 4 inverse, and X becomes B cubed times A inverse times B to the 4 altogether inverse. All right. So hopefully this gives you some idea of how to perform certain inverse properties to obtain the representations of a matrix. In practice, this skill is actually very useful, especially for numerical method, which use a lot of linear algebra to before input the data into the computer, you need to actually manipulate certain matrices, obtain the representations of that matrix, those matrices again before you input the data in. All right, so that's it for matrix multiplications. So in the next part, we're going to talk about system of linear equations. We can turn system of linear equations into the matrix equations, which we already see that in the last lecture, that you can turn the system into the equations of the form A times X equal to B. Okay, and the solutions that you obtain from the system of equations is unique. Okay, so that's the theorem that we want to focus on, and we're going to do a quick proof for this theorem. So if A is an invertible matrix, then the system of linear equations AX equal to B has a unique solutions, and the unique solution has to form X equal to A inverse times B. And to obtain X, we're going to do the similar procedure as we did from last example, that we're going to do the left multiplications on both sides of the equations by A inverse. And we're going to see that in a minute here in the proof. So the proof. So since A is an invertible matrix, A is a non-singular matrix. Right. So it requires that so that we can actually perform the left multiplications or right multiplications for that matter. So we start with the equation, the AX equal to B. And we're going to do left multiplications on both sides of the equations. And we got that X equal to A inverse times a vector B. Okay, so the solution is unique. Right. So this particular solution is the existence of the solutions. Right. And the next part is that we're going to prove that this solution is unique. Right. So the solution is unique because if x1 and x2 were two solutions, then we could apply cancellations properties to get, right. So if x1 is the solution and x2 is also the solutions, then you have x1 equal to A inverse times B, and x2 is equal to A inverse times B as well, or AX1 equal to B and AX2 equal to B. And because both equations, or the two left-hand side here, equal to the same value, which is B, then it implies that AX1 equal to AX2, but A is the same, or x1 is equal to x2. Therefore, the solution is unique, right? So the solutions of this particular system, given that A is invertible, is unique. Okay. So we classify that if A is an invertible matrix, then the system of linear equations of the form AX equal to B has a unique solutions, and the unique solution is of this form. Sorry, I forgot vector B here. In the next theorem, we have something called the fundamental theorem of invertible matrices. And all of these statements that we're going to write down are equivalent to one another. So the first four are going to make sense to us because we already cover a lot of the materials related to the first four properties. The last one is just part of the theorem, so I want to include that in there, but it's not going to make sense because we didn't go over that at all. Okay, so the following statements are equivalent. Right, so the first statement is A is invertible. So if A is invertible, then AX equal to B has a unique solutions for every vector B in Rn in this case. And the homogeneous system has only trivial solutions. Right. And the reduced row echelon form of A is actually the identity matrix, or the n by n identity matrix. So all of this four statements make sense to you, or hopefully makes sense to us in general, that when A is invertible, and the equation AX equal to B has a unique solution, and we already proved that earlier. The third statement is that the homogeneous only has only trivial solutions. That means X is equal to 0. Right. So let me quickly note that. So trivial solution in this case means that X is only equal to the 0 vector. Right. And if you actually perform a Gauss-Jordan eliminations method on A, you're going to get the reduced row echelon form, and that is going to be the n by n identity matrix. And the last statement, not going to make sense to you, I just want to include that in here. It's just part of the theorem. So A is a product of elementary matrices. So the reason is that we didn't cover anything related to elementary matrices, so it's not going to make sense to us. Right? So I'm just going to get rid of that. It's just part of the theorem, and I want to include that. That is the only reason. Okay. All right, so moving on to the last two examples. So in this example, what we're going to do is we're going to solve for the solution of the system using using this particular theorem that if A is invertible matrix, then the system has unique solutions. Okay. So first thing first, given the system x1 plus 3x2 equal to 1 and 3x1 minus 2x2 equal to 14, what we need to do is to obtain the coefficient matrix and write the system as a matrix vector form. Okay. And then part B, determine the inverse of A using Gauss-Jordan method. We already covered that in one of the previous examples. And then we're going to use the inverse matrix to solve for the solution of the system. Okay, so part A, I'm going to form the coefficient matrix. Right, the coefficient matrix is A equal to 1, 3, 3, negative 2. And so the matrix vector form of the system is, right, so you have the coefficient matrix multiply with x1, x2, and this is going to be equal to the right hand side, which is 114. So that's the matrix vector form. Now part B, what you do is we're going to determine the inverse of A using the Gauss-Jordan method. And of course, either you can do this by hand or you can use Python to help you with the calculations. So let me set up the matrix here that I'm gonna do it by hand for this particular case. In the next example, we're gonna use Python to help with the calculations. Okay, so I'm gonna form the augmented matrix. One side of the matrix is the coefficient matrix, 1, 3, 3, negative 2. And on the other side of the vertical line, you have the identity matrix. So you start by looking for the leading one in the first row, and we already have that, right? The leading one is right here. Now you need to turn this into a 0, so we need a 0 here. Okay, and to do that, you're going to take negative 3, multiply with R1. We borrow R1 in this case, plus R2 to create a new R2. So row 1 remains the same. Row 2 becomes 0, negative 11, negative 3, and 1. Okay, now we're done with the first row, right? You have the leading one in the first row and the entry below it is 0. Now you move on to the second row. The leading one needs to appear here. So we need 1 here. To obtain 1, what you do is you multiply the second row by, so multiply the second row by negative 1 over 11, right, to obtain the new row 2. So row 1 remains the same. Row 2 now becomes 1, 3 over 11, and negative 1 over 11. Okay. So to obtain the 0 entry above the leading one, so we need a 0 here. Right. So to obtain the 0 entry there, what you do is you take negative 3, multiply with R2 plus R1 to create a new R1. Right. So row 2 remains the same, 0, 1. 3 over 11, negative 1 over 11. and row 1 now becomes 1, 0, 2 over 11, and 3 over 11. Okay, so at this point, the augmented matrix becomes this, right? So on the left-hand side of the vertical line, you have the identity matrix, the 2 by 2 identity matrix. Right, so 2 by 2 identity matrix, and this is the inverse of A. Now you can conclude that the inverse matrix is A inverse equal to 2 over 11, 3 over 11, 3 over 11, negative 1 over 11. All right. Or you can take 1 over 11 as the common factor. And you have 2, 3, 3, negative 1. All right. And we're going to use this inverse matrix to solve the solutions of the system. Remember, because A is invertible, the system has a unique solutions, and the unique solution is of the form x equal to A inverse times B, for A is equal to 1 over 11 times 2, 3, 3, negative 1, times B, the matrix column is 1 over 14. So 1, 14. Okay. Now, if you do the matrix multiplication for these two matrices, what you're going to get is the vector, or sorry, the column matrix of the form 44, 11. Or the solution of the system is 4, negative 1. Sorry, this is negative 11. Right. So you conclude that the solution of the system is x1 equal to 4 and x2 equal to negative 1. Okay. So let's go to the code again and look at Python and see if we can produce the same result for inverse of A. So in this case, you have example. So example 6. Right, so example 6, what we want to find is the inverse of the matrix A, right? So there's two ways to do that. Either you use the, you create a, in this case, a 2 by 4 matrix and find the reduced row echelon form, or you can just use this command to obtain the inverse of the matrix A. So I'm just going to do that. So the matrix, let's say I'm going to call it A1 to be this, so that I can distinguish between A1 and A that I got up here. Okay. So the array that you need to create is the 2 by 2 matrix. So the coefficient matrix is 1, 3. The second row is 3, negative 2. All right. And to obtain the inverse, so A1 inverse is equal to ln alg dot inv of A1, and I'm gonna print out A1 A1 underscore n. See what happened. So as you can see, this look like the decimal places, right? So what I'm going to do is I'm going to type matrix in front of this. So apparently doing this way give us the decimal points only. So if you want to see the fraction form of the matrix, so I guess we have to create the augmented matrix. of the form. So array. So you're going to create the matrix 1, 3, 1, 0. And the second row is 3, -2, 0, 1. And we're going to do matrix D, reduce row echelon form, and just choose the first entry of the output. So, follow this manner, then you can see that the inverse of the matrix is of this form, right? In fraction form, because we do it symbolically. So that's why we have that fraction form. When doing linear algebra, formula like this, it's only give you a decimal numbers. Okay, so we show that we obtain the correct inverse matrix. Okay, now in the next case, in the next example, I'm gonna do the same thing, but we don't have to perform the entire Gauss-Jordan elimination method. I'm just going to use Python to help us with the calculations. All right. So part A again is to obtain the coefficient matrix. So A is equal to 3, -1, 1, 3. And the matrix is vector form is 3, -1, 1, 3 times x1, x2 equal to -5 and 5. Okay, so for B, you need to determine the inverse of A using Gauss-Jordan elimination method. Again, what you can do is can either use two different cases. One case you can use lialg.inv to obtain the inverse using this way, but in this case you only have the decimal points. Or you can do solve the augmented matrix using reduce row echelon form command, and they give you the value of the inverse in symbolic form. All right, so I'm gonna form the augmented matrix. It's going to be 3, -1, 1, 3, 1, 0, 0, 1. And I'm going to say that using Python. All right, so I'm gonna use a matrix E array of 3, -1, 1, 0, and 1, 3, 0, 1. I'm gonna do matrix E dot rref and choose the first entry only. So I forgot to open bracket, close bracket here. All right, so I obtained this reduced row echelon form of the augmented matrix. Where you have 1, 0, 0, 1. And this is 3/10, 1/10, -1/10, 3/10. Okay, so this is the 2x2 identity matrix, and this is the inverse of the matrix A. So you say that the inverse of the matrix is A inverse equal to 3/10, 1/10, -1/10, 3/10. Or you can take 1/10 as the common factor, multiply with 3, 1, -1, 3. All right, so now in the next part, what you do is you're going to take this inverse and obtain the solution of the system. Again, the theorems say that if A is an invertible matrix, then the system AX equal to B has a unique solution, and the unique solution is of the form X equal to A inverse times B, or A inverse is 1/10 times 3, 1, -1, 3 times B. So B in this case is going to be -5 times -5, 5. And from the matrix multiplications, we can obtain that this is 1/10 times the matrix column matrix 10, 20, or the solution is 1, 2. So the solutions of the system is x1 equal to 1 and x2 equal to 2. All right. So that's it for me for this lecture. So in this lecture, we'll look at the inverse matrix of a given matrix, of a square matrix. We went through a few examples, how to obtain the inverse of a 2x2 matrix and of the 3x3 matrix, both with the formula and with Gauss-Jordan eliminations method. We went over some properties of inverse of matrix, and we also use inverse of a matrix to solve the solutions of a system. Right? And remember, when the coefficient matrix is invertible, then the system AX equal to B has unique solutions. So that's it for me. Please let me know if you have any questions. Thank you.